Today, in Physics Myths Busted, we're going to examine the myth that light changes frequency when it refracts. During refraction, we know that light changes speed as it enters a substance. This change in speed is represented as a ratio called an index of refraction, where light speed in a vacuum is placed over light speed in the new substance. In water, we know that the index for refraction is approximately 1.33, greater than 1. This means that light travels slower in water than it does in a vacuum, or air for that matter. We know that light's velocity is determined by both its wavelength and its frequency. In fact, velocity is equivalent to wavelength times frequency. In order to lower light's velocity, then, either the wavelength, the frequency, or both those variables must be lowered. So does light's frequency change as it refracts? Well, we know that light's frequency determines its color as well. We don't believe that the frequency changes during refraction, mostly due to anecdotal evidence. We don't see colors changing underwater or when they go through windows. In order to test this experimentally, however, we are going to shine colored light through a prism and see if the color changes in the refracted beam. If it does, then the frequency is changed by refraction. However, if it doesn't, perhaps the myth is busted.
Hello. Here we have our prism and our light box. Our light box is producing yellow light. According to our hypothesis, when we place this prism in front of this light beam, causing it to refract, the color should not change because the frequency should be unchanged as well. Let's find out. Notice, it goes in yellow and it comes out yellow.
As we saw, the color of the light did not change between incident and refracted rays. So the myth is busted, right? Well, perhaps not. We know that the equation for refraction is the first index of refraction times the sine of the incident angle is equivalent to the second index of refraction times the sine of the refracted angle. Therefore, indices of refraction are independent of the angles produced during refraction. And therefore, a measurement of color, say, after the refracted ray leaves the prism, could not be compared to that before it enters the prism, as they are both traveling through air. Even though the angle doesn't change, the light returns to the same speed. However, even if we looked at the light inside the prism, our measurement wouldn't be accurate, as that light would have to travel through air to reach our eyes. And even if we, say, measured the color of light underwater to the color of light above the water, they would still look the same to us regardless of whether refraction changed frequency. Why? Because both lights would have to travel through our eyes, which contain a vitreous gel. So, in conclusion, our experiment didn't provide us with an answer. A much more comprehensive and complex test is needed to verify or bust such a seemingly simple myth.